Courses in the cement industry. Present to you. In this topic discusses, important production, troubleshooting for rotary kiln. Kiln emergency conditions. Part 3. This course contains Part 1. Part 2. Part 3. 12. Snowman in the first stage of the cooler. 13. Rush of clinker materials in the kiln. 14. Power failure. 15. Loss of kiln feed. 16. Preheater cyclones blocking. 12. Snowman in the first stage of the cooler. Snowman can frequently formed, in many rotary cement kilns, directly under the nose ring segment, in the cooler first stage. The snowman can be formed, due to the following reasons. 1. Kiln burning zone, extremely overheated. 2. The material change from normal, or hard to burn to material easy, or very easy to burn without taking notice, by the operator to make the proper changes, in the kiln to accommodate the new material. 3. The air cannons in the area under the kiln nose ring, are out of order or weak, therefore permit the clinker, to accumulate in the cooler first stage. 4. Fixed plates in the cooler first stage, are not provided with enough air for aeration, when the cooler has a CIS type of stationary plates. Consequences. 1. If the snowman is not be broken during operation, from cooler side door in the cooler first stage, the immediately stop the cooler, and the kiln to clear the snowman. 2. Lost production from kiln. Action to be taken. 1. Try to break the snowman, and if not possible try to move it, to the end of the cooler to break it, by jackhammers after stopping the kiln. 2. If the snowman breaks into medium-size pieces, then continue operation in the normal way, and follow it until it nearly reach the clinker crusher, then slow the cooler, and break it piece by piece, in order to prevent the crusher from jamming. 3. Inspect the air cannon, in the cooler area. 4. Contact the lab and see if there is any change, in the burnability of the kiln feed. How to prevent such cases. 1. The lab must contact the kiln operator, to give him information about burnability factor, and burnability index changes in the kiln feed. 2. The operator must be aware, that this information is vital to him, because it has direct impact on the kiln conditions. 3. Air cannon must be checked on daily basis, in the kiln area, and any malfunction, should be rectified. 4. If there is a camera in the cooler first stage, the operator must use it to see, if any snowman started to appear, and get an early help to destroy it. Briefly. Reasons. 1. Raw material burnability. 2. Burning zone condition. 3. Cleaning devices, in cooler and air rate. Possible consequence and dangers. Kiln production rate. Recommended action. 1. Snowman breaking. 2. Burnability checking. Preventive measures. 1. Kiln feed burnability control. 2. Air cannon observation. 13. Rush of clinker materials in the kiln. The rush of materials in the burning zone can be due to broken large ring directly after the burning zone in the area of upper transition zone, or inside the kiln in the calcining zone. The presence of such phenomenon can be known by 1. Visual observation of large material pieces in burning zone. 2. Sudden drop in kiln inlet pressure. 3. The oxygen percent in the kiln inlet drop. 4. Kiln hood pressure starts to change, and overpressure, positive pressure, can be detected in this area. 5. The kiln torque starts to change and fluctuates. Consequences. 1. Overloading cooler with a mix of clinker and unburned materials. 2. Flow of big amount of materials to the kiln burning zone. 3. The possible of damage to cooler drives and cooler components will be there. 4. Cooler crusher may jam. 5. Very hot clinker may leave the cooler. Actions that can be taken when the quantity of materials is very high. 1. Reduce kiln speed to minimum, to protect the cooler from overloading. 2. Reduce ID fan speed, and reduce fuel rate in the same time, to control the temperature of kiln inlet. 3. Reduce grate speed, after change control to manual. 4. Increase the airflow to the cooler, to ensure that the maximum cooling will be reached with cooler charge, but keep in mind that never permit overpressure in the kiln hood. 5. Keep vigilant watch over cooler, to be sure that it will work smoothly, and control the operation of the cooler, in such a way to avoid possible overloading, overheating, or jamming of cooler crusher. How to prevent it from happening again. 1. The main burner should be used, to prevent such cases by manipulating it. Repositioning the flame inside the kiln, from one day to another can do this, if the occurrence of such ring is frequent in the kiln. 2. The lab must be contacted, to evaluate the chemistry of the kiln feed. 3. If the kiln stops for any long period, and there was a ring inside the kiln, destroy it. Briefly. Indicators. 1. Burning zone observation. 2. Kiln drive amps. 3. Kiln inlet pressure and O2%. Possible consequence and dangers. 1. In cooler drives and grates. 2. In burning zone condition. Recommended action. 1. Kiln speed, and ID fan speed. 2. Cooler speed, and airflow. Preventive measures. 1. Flame position. 2. Kiln feed chemistry. Power failure. In any cement plant, the possibility of power failure is not frequent but still can happen. When the power is cut suddenly, it means all the equipment are fully loaded. In order to protect it, there should be an emergency source of power, to supply power to certain number of equipment in the plant. This include the following. 1. Kiln auxiliary drive to prevent deformation of kiln shell. It can take the shape of banana, or the shape of crank, if it is left for a long time without rotation. This is very damaging to kiln shell, and its pile stations. The operator should start rotating the kiln, in less than 10 minutes, after the power failure 1/3 of a turn, or 1/4 of a tum. 2. Primary air fan to cool, the main burner lands. 3. Cooling fan of nose ring segment, in the kill outlet area. 4. Cooler's first fan giving air, for the compartment directly receiving material, from the kill. 5. Control units in central control room, such as the computer of data logger. 6. Cooling units of the X-ray spectrometer in the lab. 7. Cooling unit for the TV camera in the kill hood. 8. Lighting system in the plant, in the critical areas such as control room, and MCC rooms contain electrical equipment. When the power supply is on again, the kill department equipment should be started in its normal sequence, to empty it from materials, and it starts with the clinker conveyor, and the cooler, then followed by other equipment. The kill should properly heated up, before start feeding. Attention! The plant emergency power generator should be tested once per week, to test its reliability. This is a must in any cement plant, or there will be severe consequences. Briefly. Quick action. 1. Kill rotation. 2. Nose ring, and main burner cooling. 3. X-ray cooling unit. Kill group sequence. 15. Loss of kill feed. Loss of feed in the kill can happen, in the kill as a result of the following. 1. No available kill feed, in the storage silos. 2. Extraction from storage silo is either hard, or erratic due to problem in the system. 3. Transportation system of raw meal, from silo to kill feed bin is out of order. 4. Kill feed dosing system facing problem, either mechanical or electrical. 5. Transportation system of kill feed, from the dosing system to the preheater top cyclones, is facing problem. When the flow of material is erratic, that means there is flow of material, but not constant and continuous. This is very dangerous to the kill burning zone, and to the heat profile in the preheater. The operator always keeps fuel rate, in the kill burning zone in the range, that is keeping the burning zone thermal load in the range, that permits liquid phase formation in this area regardless, the amount of feed introduced in kill at that time. If he decreases this fuel rate, the kill can cool down. The reason behind this is that he wants to be sure that in the end he will have clinker. Therefore he introduces fuel rate enough for that purpose. That is okay, but in reality the kill is overheated, since the kill will face intermittent shortage of feed, due to unstable and changeable feed rate. The direct result is overheated burning zone. In such condition it is important to judge the situation correctly and rationally. If this situation continues for a long period of time, then it is the duty of the operator and his team to find quick solution to the problem. If this is not possible, then he must stop the kill, to protect the burning zone refractory from possible damage. If preheater cyclones are overheated, then the possibility of jamming of the cyclones will be there. Since overheating, especially of lowermost cyclones, leads to cake formation in their cones, and eventual blocking of these cyclones. When there is no feed. 1. The operator must not operate the kill without feed for more than 10 minutes. 2. If he continued to operate the kill, as if the kill is in normal conditions, then the coat in the burning zone will start to melt and washed out, and the brick may be severely damaged, and the kill will end having red spot. 3. The second reason for this is that the top most cyclones will have extreme high temperature, and can exceed 450 degrees C, and this will damage the ID fan impeller and shaft. This is unacceptable, in any case or situation. Briefly. Reasons. Kill feed system condition. Possible consequence and dangers. 1. Burning zone condition. 2. Kill lining. 3. In preheater cyclones and ID fan. 16. Preheater cyclones blocking. Short dry kills with preheater, and with precalciner can't work in any way possible, without the preheater or the precalciner. The proper condition of these parts of the kill is vital to achieve the maximum capacity. One of the main problem in the preheater is not loss of a flap gate or inner pipes. This is rarely happen in any cement plant, but the blocking of cyclone, or more with kill feed materials. This blocking can also starts at the flap gate mounted on the feed pipe coming out of the cyclone. The blocking can start in the area of elbow in these feed pipes. Also, the area connecting the feed pipe to the cone of the cyclone is frequently prone to create problems ending with cyclone blocking. Indicators for this case. 1. Loss of negative pressure in the cone of the cyclone. If the pressure in the cone is 230 millibar, it will go down to 30 millibar or even 0 millibar. 2. Temperature increases in the riser duct, receiving the material from this cyclone. 3. Temperature increases in the cyclone receiving the gas, and the feed materials transported to it by the above-mentioned riser duct. 4. And gradually the temperature of the cyclones under the block cyclone will start to go up. 5. Also in the cyclones in the upper area, above this cyclone will start to increase. Consequences. 1. If the operator is not able to detect or continue to work, and ignores different signals that indicate the presence of blocking, the situation will go from bad to worse. 2. The kill can be shut down, for day or days. 3. In some instances the blocking is so huge, that complete cyclones are full to the level of inner pipe at the roof of the cyclone. Why blocking is happening in cyclones? 1. Overheating of the lower part of the cyclones, which can be caused by a. Absence of flap gate mounted in the feed pipe receiving the materials collected in the cone of the cyclone. b. The absence of material for some time from the preheater tower different parts, for any reason without taking proper measures to control the temperature. c. In case of the precalciner don't have materials for any reason, then the cyclones that receives the material from it will suffer from high temperature conditions. This type of blocking in many cases will not be hard but easy to remove. 2. Build-up due to the circulation phenomenon. a. This build-up will be found in the kill inlet, kill riser ducts, feed pipe out of each cyclone, and the cone of the cyclone. b. This type of blocking can be very quick in the rate of build-up of the material. c. This type of blocking the material will be hard and sometimes very solid and hard to break. 3. Structural problem inherited in the preheater from the start-up of kill system. a. There will be some faulty structures that will make the build easy to start. b. This type of problem can be found in the upgraded kills. c. This type of problem can continue for very long time with the system until a solution is found. Possible actions to be taken. 1. If the build-up that leads to blocking is not discovered and detected, then it is always very late to take action. 2. In most cases the kill will be shut down to clean the cyclone or any other part that is affected by this blocking. Preventive measures. 1. The kill should be stopped immediately, or maximum after 10 minutes, when there is shortage of materials. 2. The bypass system should be always cleaned, and operating in the proper way. 3. Lowermost cyclone must not have sulfur concentration more than 2%. 4. Flap gates mounted on the feed pipes must work properly. 5. Preheater must be in operation and calibrated. 6. Air cannon can be installed in the different parts where there are frequent blockages. 7. This can help, but it will not cure or eliminate the problem. Briefly. Reasons. 1. Lowest cyclone overheated. 2. Material buildup in cyclones. Possible consequence and dangers. Kill production. Indicators. Cyclones, cone pressure and temperature changes. Preventive measures. 1. Blocking cleaning. 2. Kill shutdown. 3. Kill feed rate. 4. Bypass system. 5. Cleaning device in preheater. Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.